Hey Geometers, welcome back to another video lesson with Mr. Forster. Today we're going over sections 8.2 and 8.3 from the textbook, going over the triangle similarity theorems. So without further ado, let's go ahead and get started. Our first similarity theorem is called the angle-angle similarity theorem, or AA for short. And it states that if two angles of one triangle are congruent to two angles of another triangle, then the triangles are going to be similar. So here in our diagram, we have triangles RTS and LPM. And because angle R is congruent to angle L, and T is congruent to angle P, we're going to have that triangle TRS is similar to triangle PLM. And a reminder, similar means they're the same shape, but usually different sizes. Part 2 here, it says we need to determine whether or not the two triangles to the right are similar. So we have triangle CDE and triangle HGK over there. And they're both right triangles, and we know that angle C is 26 degrees and angle H is 64 degrees. So what I did was I used the fact that I can find the measure of angle K by taking 90 and subtracting 64, and that gives me that angle K is 26 degrees, which means yes, they are similar. And our similarity statement could look something like this, that triangle CDE is similar to triangle KGH. You could also use some different orders, so you could say DCE, and then that would correspond with GKH. There's a few different ways that you could rearrange those, but something where they match and are lined up in the same positions like mine are. And then how do we know this is true, that they're similar, is, well, the angle-angle similarity theorem. We have two pairs of angles. In fact, we could argue that all three sets of angles are congruent to each other. Here on number 3, it says show that the two triangles are similar. So for part A, I'm showing that triangle ABE is similar to triangle ACD. And triangle ABE is this smaller triangle up here. ACD is the larger triangle, so AB is actually inside of ACD. And one of the ways that we can do this is, well, we know that they have the same measures at angle ABE and angle C of 52 degrees. The other thing that they have is they both have angle A as part of them. So A is in the first triangle, the smaller one. Angle A is also in the larger triangle. And so they would share that same angle. So it's kind of like a version of our reflexive property, but for angles. And so since those angles are congruent and both triangles share angle A, that means that they have two angles that are congruent. So by the AA similarity theorem, you could say that they are similar triangles. You could also use the fact that these two being congruent implies that these two segments are parallel because these are corresponding angles. And you could have used the fact that angle AEB and angle D would also be congruent. For part B, we're explicitly told that SR is parallel to TU, so I can use that. And I can also use these angles here, which are vertical angles. And that gives me enough for my angle-angle similarity theorem. So since angles S and U are congruent by alternate interior angles, and angles TVU and SVR are congruent by vertical angles, then the triangles are similar by angle-angle similarity. And again, you could also use angles R and T, so R and T would also be alternate interior angles, and so we'd be able to say that those two things are congruent. This is a typo. This shouldn't say converse, it should be theorem, but again, I'm not too worried about the difference between converse and theorem for our purposes. Number 4 says we have another similarity theorem that is the side-side-side similarity theorem, or SSS for short. And this one states that if the corresponding side lengths of two triangles are proportional, then the triangles are similar. And we do need to show this for all three sets of sides. So our task here for number 5 is to figure out, is either triangle DEF or triangle GHJ similar to triangle ABC? So what we can do is we can compare by finding ratios of the corresponding side lengths. And so we're going to set up proportions to make sure that all of these things are equal to each other, or set up some ratios to see if all the side lengths are proportional. We can start by looking at the shortest sides, which are AB and DE. And if I put the larger value on top, I get 8/6. and that gives me a scale factor of 4/3 when simplified. If I look at the longest sides, which are 16 and 12, those also simplify to 4/3. And then finally, the last pair of sides, BC and EF, will also simplify to 4/3. So in this case, yes, all the ratios are equal, so triangle ABC is similar to triangle DEF. And yes, if we have this type of question on a quiz or a test, you do need to show all 3 pairs of side lengths, because you need all 3 for side-side-side similarity theorem to work. Continuing on number 5, we can do the same thing and compare triangles ABC and GHJ, again by finding ratios of the corresponding side lengths. I do want you to work through this for a moment and try it on your own, and then I will reveal my solution. So take a few moments, pause the video, and try it on your own. All right, I'm sure at least half of you paused the video and actually tried it on your own. To the other half that are just waiting for me to reveal the answer, no, really, you should pause the video and try on your own. I'll wait again. Okay, for the 2 extra people that I convinced to actually try on their own, you could check your work now. For the rest of you that inevitably are just waiting for me to say the answer, here is my solution. The shortest sides, AB and GH, are 8/8, which is 1. The longest sides, CA and JG, are 16/16, which is also 1. However, BC and HJ are not equal to each other, so the remaining sides have a ratio of 6/5, which is not 1. So in this case, they're not equal, and these triangles are not similar. For number 6, it wants us to find the values of find the value of x that makes triangle XYZ similar to triangle HJK. And for this one, we want to be able to show that all 3 of the ratios are equal. And we can set up proportions to solve for x, assuming they haven't set us up for failure, and in this case they haven't. We can just set up one of the proportions. We could go a little bit further and show the other pair of sides, but in this case it does work out, and you can test it for yourself here in a little bit. I chose HJ over XY because I know those 2 values of 15 and 3, and HK and XZ because I thought that 30 over x minus 5 was a little bit simpler than the other pair. And if I use my cross multiplication, I take the 15 and the x minus 5, and they go together on one side. 3 and 30 go together on the other side. And when I multiply out and distribute the 15 to both the x and the minus 5, I get 15x minus 75. On the right side, I get 90 from 30 times 3. We can add 75 to both sides, leaving 15x equals 165. And then if we divide by 15, we should get that x equals 11. So our ratios should simplify down to 5/1 for all 3 of the pairs of sides, because that's what 15/3 simplifies to. And if we look at our 30 over x minus 5, that would be 30 over 11 minus 5, which is 30 over 6, which does simplify to 5/1. And we could also have shown that these 2 are equivalent. HJ over XY is equal to JK over YZ. I want you to check that one on your own, so plug in the value that we got for x and make sure that this is true. Number 7 states the side angle side, or SAS, similarity theorem. And it states that if an angle between 2 sides of one triangle is congruent to an angle between 2 sides of a second triangle, and that those sides are proportional, then the triangles are similar. So again, the angle is that included angle, so it has to be in between the 2 sides, and the sides have to be proportional in order for this to work. So just like we did with congruence theorems back in Unit 4, side angle side is also a similarity theorem. For number 8, it says show that the triangles are in fact similar. So we have triangle SRT and triangle PNQ. I do have a right angle for both, so I know that they have the angle is congruent, and the angle is in between the 2 legs of each of the triangles. Since they're right triangles, we call these the legs of the triangle. So we need to just check to see if they're proportional. The shorter sides, which are 24 and 18, SR and NP, simplify to 4 over 3. The longer sides, which are RT and NQ, also simplify to 4 over 3. So that would be enough information for us to say that these are similar by the SAS similarity theorem. For part B, it's a little bit trickier. So I want you to take a moment and try this one on your own and see if you can set up the right proportions to show that these two triangles are in fact similar. And I will reveal my solution here in a moment. No, really. Try on your own. Hit pause, write things down, try on your own, and then come back. I'll wait a little bit longer. Okay, I'll reveal my solution. The shortest sides of the two triangles, XZW, this one right here, is XZ, so that's going to be 12. And then YZX is this small triangle over here. Its shortest side is YZ. So I would use 9 and 12. And the reason that I would use those as the two sides is this angle right here, WZX, is also going to be a right angle right there. The longer sides, which are WZ, it's the longer side that's sandwiching that angle there, and XZ, which is the longer leg that is sandwiching the angle, because we're using side angle side, is 12. So we have 16 over 12, and that also simplifies to 4/3. I know this one was a bit tricky, so if you have questions on this one, feel free to let me know when I'm back tomorrow. But again, we have our two sets of sides that are surrounding our right angles, and they both simplify to the same ratio, so these triangles are similar by side angle side similarity. All right, number 9. We have a flagpole that is casting a shadow, and that shadow is 50 feet long. So that's the shadow over here. And note the not drawn to scale, because my drawings are never appropriately drawn to scale. And then it says, at the same time, a woman who is standing nearby, who is 5 feet and 4 inches tall, that's our lady over here, is casting a shadow that is 40 inches long. So her shadow is 40 inches long. We want to know how tall is the flagpole. And the reason that we can use her height and her shadow length is if the sun is at the same angle, then these two triangles that are made by the flagpole and its shadow and the woman and her shadow would be similar. So what I did first is I converted everything to the same units. And I have the flagpole's shadow length over here. It's going to be the 50 feet times 12 inches in each 1 foot for a grand total of 600 inches for the flagpole shadow. For the woman's height, I take the 4 inches because she's 5'4", and I add the 5 feet, again multiplied by 12. So 5 times 12 is 60, plus the 4 gives her height is a total of 64 inches. And then from there, I can set up a proportion to solve for the height of the flagpole. So the proportion that I would set up is the woman's height, as it relates to the flagpole's height, is going to be equal to the woman's shadow length divided by the flagpole shadow length. I used h for my variable because h made sense for a height. And that would result, if I use everything in inches, 64 is her height divided by h is equal to 40, which is her shadow length, divided by the 600 inches that we found for the shadow length of the flagpole. And then cross multiplying gives me 40h will be equal to 64 times 600, which 64 times 600 is 38,400. And if I divide that by 40, I get a height of 960 inches. Now, it asks for the nearest foot, so I need to convert everything back to feet. So 960 inches times 1 divided by 12, or divided by 12, and I get a grand total of 80 feet tall. So the flagpole is 80 feet tall. All right, number 10. Ramon places a mirror on the ground and walks back until he can see the top of the geyser in the middle of the mirror. It wants us to use similar triangles to find the height of the geyser. So I want you to try this one on your own with your table groups, and I will reveal the answer here in a little bit. All right, for those 3 of you that actually did this on your own and didn't just wait for me to reveal the answer. I appreciate you. For the rest of you, slackers, we're going to set up a proportion to solve. I set it up as 6 feet over x, because that's the height of the geyser and the height of Ramon, is equal to 7 feet over 40.5 feet, because that's the distances from the mirror. And then I can multiply 6 and 40.5, put that on the right, 7 and x, put that on the left for my cross multiplication. And that will simplify to 7x equals 243, which means x is approximately 34.7 feet, or 34 and 5/7, I believe is what the fraction is if you went with the fraction version. All right, your assignment, which is in the packet, is the lesson 8.2 and 8.3 homework sheet. Good luck, do well, and I will catch you in the next one.